More problems from Chapter 8. Number 16, we're going to drop a 700-gram block, that's 0.7 kilograms, onto a spring with a spring constant of 400 newtons per meter from some unknown height, and the block sticks to the spring and momentarily stops after compressing the spring 19 centimeters. How much work's done by the block on the spring? How much work done by the block? The force of the block on the spring would be downward, and it's moving downward, so that's positive, right? So the work done by the spring is would be that 1/2 kx initial squared minus 1/2 kx final squared. But we know that since it's being compressed from nothing to this much, that the work done by the block is going to be equal to the total amount of energy that's stored in the spring at that maximum compression, right? Because of the conservation of energy, right? So where was the energy at the start? It's in the block, the kinetic energy of the block, and when it momentarily stops, all the energy is in the spring, right? So the work done on the block, on the spring by the block, is going to be equal to this. So 1/2 k x squared, and that is equal to 7.2 joules. You can check my work there. Right now, let's just run it quick. 200 times 0.19 squared. Yep. And again, that would be positive because the force of the block on the spring is downward and it's going downward. How much work did the spring do? The spring did negative this much work, right? Because the spring force is up, the block is moving down. And that's the answer for part B. Negative 7.2 joules, right? So it's kind of an extension of the equal opposite force, right? Equal and opposite work. C, what's the value of H sub 0? Where was it dropped from? Well, how much, at the beginning, all of the energy is gravitational potential if we're dropping it. And at the end, all of the energy is in the spring. And we know how much energy is in the spring, 7.2 joules. So that means mgh is equal to the 7.2 joules. The mass is 0.7 times 9.8 times that unknown height, equal to 7.2 joules. So you have 7.2 divided by 0.7 divided by 9.8, which is about 1.05 meters. And that's above the max compression. And let me just see if what they asked for here. They asked for, so if they want to know it's released from that much above the spring, so since the spring got compressed by this much, the height above the spring when it wasn't compressed would be 1.05 meters minus the amount that it got compressed. Right? What we found was the height from all the way from the very beginning to the very end of the problem, but the spring got compressed 19 centimeters, right, to here. Spring started here and got compressed. So if they want to know how high above here, would have to subtract off that 0.19 meters. And that's going to give us, what is that going to give us? 0.86 meters, right? And then part D, if the block were released from a height of 2 times that, what would be the maximum compression of the spring? So let's see, now we're going to, it's the same problem, right? But now we're going to release it from 2 times that, and that's going to compress the spring some unknown distance x. So let's see, that will give us mg times 2h. But actually, I wonder, let's do it this way, and then we'll see if we agree with the book answer. I think we're going to be a little bit off if we do this, and we'll discuss why. So we're dropping it from a height of 2 times this, 2 times 0.86, and half the k, so I plugged in all the numbers here. The mass is 0.7, half the spring constant is it 400 in this problem? Yeah, 400 x squared. It's all a blur. So let's see if we can do that. So I have 0.7 times 9.8 times 2 times 0.86, and then 1/2 400 is 200 divided by 200, and then I need the square root of that. So I get a compression of 24 centimeters now. See if the book agrees with that. Yeah. So, in fact, the thing that's a little bit off here is if we do it this way, we're saying that the amount of potential energy change is just 2h, but we're not taking into account the fact that it actually goes lower than that, right? Because it actually gets compressed too. So this gives us a good approximation, but it does not take into account the extra little bit of potential energy that it's going to give up as it descends on the spring. So really, mg, it's not descending a distance of 2h, it's descending a distance of 2h plus however much it's compressed right here, right? The same x. It's going to get compressed that much also. So that would be the actual equation. And according to the book's answers, if you do it that way, taking that into account, which you should, it's actually 26 centimeters. So if you did this and got 24, I think you made a good pass at this problem, but in fact, you would have to add that in, right? Because it's going to drop that extra little bit, right? And because it's giving up more potential energy, it's going to get compressed a little bit more. So, interesting. Let's see, 24. What do we have here? We have another block dropped on springs. Block of mass 2 kilograms is dropped from a height of 40 centimeters onto a spring of spring constant 1,960 newtons per meter. Find the maximum distance the spring is compressed. So this is just a reprise of what we just did, isn't it? We're dropping it from an h of 0.4 meters, and the mass is 2 kilograms. So let's do it the right way this time. So we know here's the block. We're going to drop it onto the spring, right? This is 0.40 meters, and but it's not just going to give this up. By the time it gets to the bottom, the maximum compression, it will have compressed this a distance x, and that means that the total change in height would be this plus that x. So all of that gravitational potential is going to turn into spring potential. How much gravitational potential? Is mg is h plus x, this height plus the x. That's going to be equal to 1/2 kx squared. Let's do that. Let's see how messy the math is. So it was 9.8 times 0.4 plus x is equal to 1/2 k. What's 1/2 of that? Is that 980? That's cute, isn't it? 980 times x squared. So this is a little harder to solve because we have x's on both sides. Let's see what it looks like when we do it. Looks like it's going to be a little quadratic equation. So 980x squared. Then if I subtract the x term over, minus 19.6x, and then minus 19.6 times 0.4, 19.6 times 0.4, 7.84. Right? And I'm going to solve this by graphing. That's the best way to deal with things like this. What the heck is that? So let's see, 980 x squared minus 19.6 x minus 7.84. And before I graph that, before you just go hitting the graph button, let's look at the window. What kind of answer are we expecting here? I'm looking to solve for this x. Now, whatever it is, I don't think it's going to be very much. That's a pretty stiff spring, right? So I'm expecting an x that's certainly less than this, right? So I'm going to go ahead and make this, well, I guess I'll make it 1. I think that's probably a pretty good window to look for our answer. And then it doesn't really matter what the y min and the y max are. I'll go with the negative 10 and 10 and graph that. And I'm expecting to see, yeah, this is 0 and this is 1, so it's way down there. And then I'm going to find that 0, and I'm not going to play with the cursor. That's a waste of time. I know for sure that the left bound, right bound, it crosses between 0 and 1. So I'm just going to type those in. 0, right bound, 1. It's somewhere on my screen, right? 0.1. So the x is equal to 10 centimeters. It's a good problem. Good one to follow up with after number 16 or whatever it was. Yeah. All right, number 27. What do we have here? Tarzan. Sweet. Who weighs 688 newtons, swings from a cliff at the end of a vine that is 18 meters long, and from the top of the cliff to the bottom of the swing, he descends by 3.2 meters. So that's 3.2 meters. Right, so there's some gravitational potential energy he's picking up there. Going to turn into kinetic energy. The vine will break if the force on it exceeds 950 newtons. Does the vine break? Well, if you've ever been on a rope swing over a river or something like that, maybe you know from experience that the force is that you feel, which is you counteracting the tension in the rope, is maximum at the bottom. And why is that? Well, that's where your velocity is going to be maximum, and that means the centripetal force required to move you in that circle is, which is mv squared over r, that's going to be maxed out because your v is maxed out. So let's see what we can do here. Definitely some force diagram stuff coming up here, but let's just figure out how fast he's going. That's an energy problem. So here we've got gravitational potential. At the bottom, kinetic energy. How much gravitational potential? mgh, 1/2 mv squared. The m's cancel out, so he's got 3.2 meters worth that he's going to give up to kinetic energy as he does his Tarzan thing. So his velocity will be the square root of 2 times 9.8 times 3.2 So 7.9 meters per second. That's how fast he'll be going at the bottom. Now, if you're moving in a circular path, right, which they kind of suggested that in case you didn't think of it, they drew a circular arc in their picture, then the centripetal force required for you to move in a circle is equal to mv squared over r. So that is, let's see, the mass of Tarzan, let's see, they gave his weight in newtons, so 688 divided by 9.8. Mass of Tarzan is about 70.2 kilograms times his velocity at the bottom, we just found that, over, squared, over r, which is what, 18 meters? So let's do that. You've got 70.2 times 7.9 squared divided by 18. So we need 244 newtons of centripetal force. You might look at that and say, well, look, the rope was going to break at 950 newtons, so we're fine, right? But no, we're not fine necessarily, because think about the force diagram here at the bottom. Centripetal force is net force, right? It's not any one particular force necessarily. So here at the bottom of the swing, we have force of gravity on Tarzan and the tension of the rope on Tarzan. So the net force, which is the centripetal force, is equal to tension minus the force of gravity. So how much tension is there in the rope? There's the centripetal force, which we found, 244 newtons, plus the gravitational force on Tarzan, 688 newtons. So is it going to be all right? Just. So the tension required is not this. That's how much the tension has to beat gravity by, right? So 932 newtons. So he is going to be okay. So does the vine break? No, it does not. If no, what's the greatest force on it during the swing? So that would be what we just found, 932 newtons. And then part C, if yes, at what angle the vertical does it break? That would be an interesting problem to try to do right there. It would be a little bit difficult, I think. But we don't have to do it because it didn't break. So no part C. In the interest of not making this video too long and my own sanity, because it's late and I need to go to sleep, I'm not going to do number 34. It's an awesome problem. And it's in parentheses because I think it's quite difficult. And for those of you who like to step up to that kind of challenge, I would highly recommend grappling with that problem. You'll learn a lot from it. And if you're not feeling it, then don't worry about that one. Okay? Oh, but you should ask me, because I have if you are interested in that problem, I have a video on my computer of a simulation of this problem with a dry ice puck on a bicycle wheel rim that shows the where you can look at the video in slow motion and see where it actually loses contact. So that's kind of cool. So if you're interested in that, ask me about it and I'll show you.